Characterization of U-233 for thorium fuel cycle safeguards will be presented by Ms. Madeline Lockhart. Doing the introduction today is Dr. Patricia Pavier. Patricia is the chair of the Gen 4 International Forum Education and Training Working Group. She's also the National Technical Director of the Molten Salt Reactor Program for the Department of Energy, Office of Nuclear Energy. Patricia.
Thank you so much, Berta. Good morning, good afternoon, good evening, everyone. It's a pleasure to have Madeline Lockhart with us today. She's a fourth-year PhD student in the Department of Nuclear Engineering at North Carolina State University. She's the winner of the American Nuclear Society 2023 Pitch Your PhD competition. Currently located in Ispra in Italy, she is spending 6 months as a visiting scientist at the European Commission Joint Research Center. She was awarded a Nuclear Non-Proliferation and International Safeguards Fellowship by the National Nuclear Security Administration in 2021 as a part of a multi-university, multi-laboratory team. She is working to develop new neutron multiplicity counting methods to assay uranium-233 and uranium-235 in mixed oxide nuclear fuel materials. Throughout her undergraduate and graduate studies, she has done research in the Nuclear Engineering and Non-Proliferation Division at Los Alamos National Laboratory. In 2019, she was an intern at the Department of State in the Bureau of Arms Control, Verification, and Compliance. Madeline has a Bachelor of Science in Physics from Texas Tech University. So without any delay, I give you the floor, Madeline, and thank you very much.
Awesome. Thank you so much for that introduction. I want to thank everyone for being here. Whether you're in the US, I know it's kind of early, or if you're in Europe like I am, good afternoon. Thanks for joining. I think we're about a week from Christmas, so I know you guys are itching to go on a holiday break. But yeah, let's go ahead and get started. So we're gonna eventually get to uranium-233, but I want to back up for a minute and just kind of give a few definitions, not too many, on what nuclear safeguards are. I do want to say that there was a previous GIF webinar in March of this year that did kind of an overview of advanced reactor safeguards. So if you're interested in nuclear safeguards, not specifically for maybe thorium or U-233, but just advanced reactors in general, I would definitely suggest going back to watch that. That gives a really good overview, and this one's going to get into a little more technical detail, looking at some of the challenges we face when we're looking to develop safeguards for new reactors. All right, so let's get started. First of all, we're going to define safeguards as a set of technical measures applied by the IAEA on nuclear material and activities. So I want to stress, technical measures. So that requires technology and methods and instrumentation used by inspectors to go and perform these verification measurements. And the objective is to deter the spread of nuclear weapons by early detection of the misuse of nuclear material or technology. How I generally describe it to, non-nuclear or non-technical or non-safeguards people is if you have nuclear energy on one side and you have nuclear weapons on the other side, safeguards is right in the middle, right? We want to make sure that all the material and technology that are used for peaceful purposes, for energy or, medical uses, whatever those are, aren't diverted for weapons. So we're kind of right in the middle. All right, next slide, please. Okay, so when we're looking to develop safeguards, it's important to understand that you don't really develop new safeguards methods or instruments overnight. It generally takes on the order of 10 years, if not longer. I want to stress most of the time it's longer than this, but this is kind of an optimistic timeline. And so what we'd like to see is with the development of safeguards methods, we want that to be kind of in parallel or concurrent with the development of new fuels or new reactors that are, looking to reach potential commercialization at some point in the near to semi-near future. And so if we're kind of looking at, say, okay, our let's see, some fuel or reactor that's being developed is, going to plan to operate in 2030. Again, that's pretty optimistic, maybe 2040. We want to be thinking about and starting to develop the safeguards methods now. That way, when that comes online in the future, we kind of already have a toolkit that can then be applied. And it's difficult because sometimes, depending on the reactor, the materials and other kind of aspects of that aren't always clear, and so it's a challenge to us sometimes to say, okay, what can we do to best prepare for when these reactors and designs are ready for commercialization. All right, next slide, please. Okay, so specifically for thorium fuel cycle safeguards, we're looking to develop proliferation detection research and development that's needed to make this toolkit that I mentioned before. So, we're looking at safeguards verification methods, remote detection, stuff like that. And these need to be ready to monitor fuel cycle activities. I'm going to reiterate, it's important that advanced reactor designers, which I hope many of you on the webinar here today fall into this category. You don't necessarily need to develop the safeguards, but we at least want you to think about them. And so as you're going through this design process, that we can kind of come alongside and see how we can best fit those into the design, and not when you get to the end and say, hey, we have this awesome reactor design, we're ready to sell it, and then the government says, sorry, you need safeguards before you can export that technology. I want to emphasize also that just because a material or a design is, quote, self-shielding or proliferation resistant, that does not exempt it from safeguards. In fact, sometimes it can actually make it harder to apply safeguards on that material, which is, a headache for the IAEA or inspectors, and also for, the operators and people who are in the reactor. And so specifically looking at characterization of 233, it's important for safeguards for any future thorium reactors that will be commercialized, but also for nuclear material accounting and control, because we have uranium-233 that exists currently in the world. And so it's important for us to be able to characterize what we already have, again, for the same reason as safeguards, to know how much material we have and, what kind it is. All right, next slide, please. Okay, so before we got into this project that I'm currently working on, there was a pretty extensive research and development needs assessment that was done by several people at several of the labs. If you're interested, again, I would encourage you to Google this title and you can find a PDF copy. And the challenge is really, they wanted to understand what technology was potentially needed, again, to build this toolkit that we've been mentioning, to look at potential candidates for thorium fuel cycles and what characteristics might, need safeguards or impact safeguards, again, material types and different kind of processes. And then looking at how we can strengthen existing instrumentation and develop new instrumentation. And you'll kind of see this theme throughout when it comes to safeguards. We have a lot of very well-established technologies and methods. And so a lot of what we're looking at is not necessarily to develop brand new methods and instrumentation, but maybe, adapt current methods or current instrumentation to meet these needs, to safeguard material with thorium or 233. All right, next slide, please. All right, so some of you might be thinking, what in the world is uranium-233? And how is it different from 235 and 238? So I'm going to assume most people kind of have a general understanding of nuclear. If you don't, we'll walk through it a little bit. But we start with thorium, right? We're talking about thorium-fueled reactors. Thorium is not a fissile material, right? You can't use it to start a chain reaction, but it is a fertile material. So it can undergo a process that results in a fissionable material, which is, in this case, uranium-233. So you start with thorium-232, it captures a neutron, becomes thorium-233, and then undergoes 2 subsequent beta decays to get uranium-233. And so that's kind of what we're looking at. Again, uranium-233 is a fissionable material. And then, let's see, in the next slide, we'll talk a little bit about what makes it different from the other isotopes. All right, so why do we care about uranium-233? I'm going to throw a few more definitions at you. I promise there's not too many after this. But the IAEA defines a significant quantity as the approximate amount of nuclear material for which the possibility of manufacturing a nuclear explosive device cannot be excluded. Right? You can look all these up in the safeguards glossary. But again, it's just, I think sometimes we don't hear these enough. And then more specifically, we're looking at significant quantities of direct use materials. So these are materials that you really don't need to do anything else for them to potentially be manufactured into a nuclear explosive device. And so this includes plutonium that has less than 80% 238, uranium-233, and then highly enriched uranium. So that's more than 20% of U-235. So if you look at this, the significant quantity for uranium-233 is the same level as plutonium. So we're worried about a smaller quantity than for highly enriched uranium. So when it comes to safeguards, again, we're concerned with a smaller amount of material potentially, being diverted than in some of the traditional reactor designs. One thing I think I'm going to talk about it really quickly. Well, no, I'll wait until later. Okay, so again, those are some of our definitions and why we care about this and why we have to safeguard it. So next we're going to talk about how do we actually, characterize these materials. Okay, I think this is the last definition, possibly, but we're going to define special nuclear material. It's nuclear material specifically that's plutonium, uranium-233, or enriched uranium enriched in the isotopes 233 or 235, but it doesn't include source material. So natural uranium is not especially a nuclear material. Again, I think sometimes if we don't hear this or no one ever explicitly says this, we don't always know the distinction. Okay, so what we want mass and isotopic composition, right? We need to know what is in, our sample and how much of it we have. So two methods that are used, we're going to talk about are nondestructive assay and destructive assay. They kind of, are a little obvious. Destructive assay is, when you take an actual sample of the material and you destroy it when you're performing different analyses or chemical analyses. This can be really great in certain situations where you want to know like the isotopics very specifically or other kind of features, but can be very expensive. It can be a long process if you have to take samples and ship them to labs that are in other states or countries often. But again, it can be highly accurate, but not always the best for what we need it for, which is it's mainly mass. And so what we're going to focus on today is non-destructive assay, or NDA, and that kind of splits into two categories, gamma and neutron. Today we're going to focus a little bit more on neutron than gamma. We're not really going to focus on gamma at all, but I'll talk in the next slide about why we focus on neutron and not so much gamma. Okay, so we don't really use gamma for characterization of U-233 because even if you have a really pure form of 233, you're likely still going to have contamination of uranium-232. And that's another, it's not the uranium-232 that is producing gamma rays, it's one of its daughters in its decay chain, thallium-208, and that produces a really high energy gamma ray. So if you have even 10 on the order of tens, hundreds parts per million of U-232, your gamma signal is dominated by that single peak. So when it comes to getting any sort of information on specific isotopics or mass, it's really just going to get taken over by that. And if any of you are familiar with using gamma to measure the enrichment of other uranium, uranium with 238 and 235, they'll use gamma. They'll look at two different peaks from each of those isotopes, and they'll look at a ratio between those peaks to determine the enrichment. That doesn't work here. And so kind of excludes that. And because you have this daughter isotope that is highly radioactive, that means a lot of times the sources are in lead shielding, which a lot of that, the point is to generally shield the gamma rays. And so if you're trying to get, some sort of mass quantification from gamma, that makes it nearly impossible. So long story short, we're going to focus on neutron. There's one interesting thing that distinguishes 233 from 235 and 238 is that it has a relatively shorter half-life. I think we'll see this on the next slide. And so you actually get, so it goes through alpha decay, and if it's in some sort of form with a light element, like an oxide, you actually get alpha N neutrons produced from a sample. So it'll decay, it'll produce an alpha particle that'll interact with the light element and give you a neutron. This is important because, so again, I'm not going to assume that everyone here is a nuclear engineer, but this type of neutron signal is a little different than what you would see from fission neutrons. Because when an isotope fissions, you get, your fission products, and then you get some neutrons. But it's not always one neutron, and most of the time it's not. Most of the time it's more than one. Generally an average of about, say, 2 point, I think, don't quote me on this, it's somewhere between 2 and 3 neutrons per fission, and that generally depends on the isotope as well. But you can get anywhere from 1 to 7 neutrons, and we have ways when we're detecting neutrons of correlating those neutrons or mathematically determining which neutrons could possibly have come from the same fission event. The difference here is alpha N neutrons are produced one at a time, and so none of those neutrons came from the same event. And so we can use that in our kind of neutron analysis, and we'll get into this a little more later. That's one feature that we can actually use to distinguish the two. There's something else we use called active interrogation. That's when you take an external source and you, don't advance this yet. Sorry. Actually, it's fine. Okay. There you go. Okay, so we traditionally use active interrogation for uranium-235. It's fine, just leave it on this one. Okay, so let's go ahead and talk about the different neutron NDA methods. So we have passive neutron coincidence counting. So that's kind of in reference to those alpha N neutrons, is that'll give us a neutron signal without any additional, sources or anything needed to measure that sample. Active neutron coincidence counting is when you take kind of an external source and you use it to interrogate your sample and produce more fission. So you kind of will interrogate the source with neutrons, and it causes additional fissions to occur, and then we can measure those neutrons coming out from the fissions and correlate them and use that to help determine the mass. And there are a few other neutron NDA signatures we're looking at, and these are a little more novel, but that work has been mainly spearheaded by my colleague Oscar Sierfus from the University of Michigan. He also works at Sandia, California, and so if some of these that I mention are of interest to you as well, I would definitely look up some of his work and papers that he's published. But we're also looking at delayed neutron signals, differential die-away, and passive neutron spectroscopy. Again, I'm not going to go into those here, but if you're interested in those, there are other resources. And then this table you'll see below, this is referring back to what I mentioned earlier, that when we're looking at the different isotopes of uranium, there are some differences. And so what we're looking at is, the half-life of uranium-233 is still pretty long, right, 10 to the 5th, but it's relatively a lot shorter than 235. And so if you look at the far right side of that table, the alpha N yield, we're looking at the number of neutrons per gram is measurable. It's on the order of about 5 neutrons per second, and that can vary depending on the chemical composition of the sample, but for U-235 it's not measurable. All right, next slide, please. Okay, so let's take a look at some of the instrumentation that we used for these. We're going to talk a little bit about the electronics because it is important, how we're acquiring this data and what these acquisition systems lets us do with the data that's maybe novel or gives us more insight into how we can use that to perform these measurements. And for those who aren't familiar with, neutron detectors or counters, you can kind of see what that looks like and how that's operated. All right, next slide, please. All right, so this is the active well coincidence counter, or AWCC. If you recall before, I mentioned active interrogation. That's where the active comes from. So this is designed to house 2 active interrogation sources, and I'll have a model of it in a later slide. You can see exactly where those sources are within this well counter, but generally they're at the top and the bottom. And then you have your sample in kind of a central cavity in the middle. It's a helium-3 well counter, so there's a bunch of helium-3 tubes. They run from the bottom to top of the well detector. They're cylinders in 2 rings around that central well. And this counter, so we actually used like an older brother of this counter called the large volume AWCC, which is a slightly scaled version of that, which has 48 helium-3 tubes. You can use it in passive and active mode. So with active, you have those interrogation sources. With passive, you just remove them. And there is a removable cadmium liner that lines the inner cavity and also goes on the top and bottom of the sample cavity. And that allows you to operate this in thermal and fast mode. And what that means is when you have a neutron interrogation source, you have a certain kind of spectrum of neutron energies that are going from your interrogation source and then interrogating your sample. When you have it in thermal mode, you don't have a cadmium liner. And for any of you that are familiar with cadmium, cadmium has kind of an energy cutoff, and it's really good at absorbing thermal neutrons. And so anywhere below, I think it's 0.25 eV, any neutron that has less energy than that, most of those will be absorbed by that cadmium liner. And so when you have that cadmium liner in, it will absorb a lot of those thermal neutrons, only allowing more of the kind of fast neutrons and higher part of that spectrum to interrogate your source, and that allows those higher energy neutrons to penetrate deeper into the source. And so this is generally used for larger samples, so maybe 100 grams or more. When you get into kind of smaller samples, you're not really concerned as much with how far those neutrons are penetrating into the samples. You're more concerned with the actual mass because it's significantly less, and so you get significantly less signal. And so when you remove that cadmium liner, it allows a lot of those thermal neutrons or lower energy neutrons to come in, and you get a better sample. So we used both modes because our samples were kind of in that middle line. There's actually another reason, but I'll show you that later. I don't want to spoil it. Okay, and then there's detector parameters, if anyone's interested. Has about 30% efficiency, so 30% of the neutrons emitted generally get captured or detected. All right, next slide, please. Okay, so this is the JSR-15. This is a traditional shift register. It essentially counts neutrons, the neutron signals as they're coming in from the detector. This is what's currently used by the IAEA for verification measurements. There is a software called INCC, International Neutron Coincidence Counting, I think for the code. And you can either operate it handheld like this person is doing here, or you can control it using a computer program. But a lot of the analysis methods and everything are already programmed into this code. So the inspectors will just go, do a measurement, put in whatever parameters are needed, and then it will spit out, different verification information. And so when you acquire data with this, there are predetermined analysis parameters. And so what's important here is that, okay, this is why the fission neutrons versus alpha N neutrons were important earlier. Remember, alpha N neutrons come out one at a time. They're independent of each other. Whereas fission neutrons, they come out in little bursts, and we want to try and correlate those together to use that to determine the mass. And so with the shift register, you kind of have parameters that are set to measure the number of coincidence count rates. So essentially what happens is when you detect a neutron, we wait a little bit because sometimes the detector needs to recover the electronics. And then we open a gate and we say, okay, during this period of time, we're going to count how many neutrons come. And we're assuming that some of the neutrons in this first gate might be from the same fission event that our original neutron was from. So we're going to count, and then we're going to wait, and then we're going to open a gate of the same size, and we're going to count again. But the second gate, the accidentals gate, is long enough away where there's pretty much no chance that any of the neutrons in this second gate is from the same fission event as our original neutron. And so when you take the accidentals and then gate and then the reals and accidentals and subtract them, that gives you the reals, which is essentially a coincidence rate. So that's essentially, think, 2 neutrons that we think statistically came from the same fission event. And so, and it can go on. We can get triples, we can get quads, pents. That requires detectors with much higher efficiency because those count weights kind of go down as a factor of efficiency. So if you have 30% efficiency to measure a single neutron, you only have 30% times 30%, or about 10% to measure 2. So that generally decreases pretty quickly when you get to higher orders. But this is important because all these analysis parameters are preset using the JSR 15. And so what we're going to do is, in addition to using this, we also used another data acquisition system that allowed us to kind of overcome this kind of limitation. So next slide, please. Okay, it might take a second to switch since we got some pictures. Okay, so this is the Advanced List Mode module, or the ALMM. It was designed at Los Alamos to perform list mode data acquisition. This is not the only list mode device that exists. There are several out there. This is the one that we had developed, but the purpose of this is to record the pulse train, which is pretty much the time and channel for every single neutron detection event that happens. And so you pretty much get the raw data. And what that allows you to do is go back after the fact and do analysis with different parameters. So we talked about gates. You can change the length of that and see how that affects your numbers and how that potentially could be used in any sort of mass determination. In addition, this allows you to get more than one channel of data. And so for our measurements, the AWCC had 2 rings of detectors. And so each ring has its own output. And so we actually were able to get the 2 signals of the inner and outer rings separately, which most of the time we're just going to put those together and analyze it all together. However, this can be really interesting if you're looking at the ratio between the 2 rings, because that can tell you information about potentially the energy of the neutrons that are being emitted. And I'm going to refer back to our conversation earlier about alpha N neutrons versus fission neutrons. Those energies are slightly different. So there could potentially be a way to use this ratio and the different energies of neutrons that are emitted to try and kind of tweeze out pieces of information. So sometimes you don't want too much data because that can sometimes be not helpful, but it's useful to have a lot of this raw data so we can kind of experiment with it. All right, next slide, please. All right, so we did do measurements of uranium-233 sources. These samples were at Oak Ridge National Laboratory and their radiation signature training devices. So they're little triangles or source tiles that were made to be configured in a kind of spherical shape by the Department of Homeland Security, and they use them, to test portal monitors and other, radiation monitoring devices. And so these are a really unique set of samples because they're all individual tiles and they each contain about 2 grams of uranium oxide, and there's a total of 40 of them. And we kind of use them as like a build your own source kit. And so we could, have the smallest sample being 2 grams, and we could build that all the way up using all of the triangles to get a total of about 80 grams of U-233. In addition, there are similar triangles, not identical, they are similar, sources that have highly enriched uranium, so it's about 93% uranium-235. And so that's really interesting because part of the challenge we have is distinguishing between the two isotopes. And so this allows us to mix them together and do measurements and see if we can come up with a method to kind of distinguish or determine how much of each isotope of uranium is in our sample. And so again, the HEU sources are not identical. They have a little less mass per tile. I think it's about 1.5 grams, so it's about a 4 to 5 ratio between the two. But again, it's super useful, and that allows us to build our total fissile mass with all of these triangles to about 140 grams. All right, next slide, please. So before we get into some of the measurements that we performed, I want to quickly go over what is traditionally used for mass verification for 235, because that was pretty much where we started. We said, hey, let's again, look at what current methods and instrumentation are used and see if, maybe we don't have to start from scratch. Maybe we can apply, current methods to this or extend those or enhance them. And so how traditional mass verification works is you perform active measurements with these AMLE sources. So on the right-hand side, you'll see the active well neutron coincidence counter. In the center there is the sample cavity, and then above and below, you'll see the 2 little interrogation sources. Outside that sample cavity, in the gray, you'll see that's one of the tubes. I think because it's a cross-cut, you don't see both rings, but there'll be another ring of tubes slightly outside of that. And so they'll do active measurements of essentially a set of sources that are all, what's the word for it? They're pretty much all the same kind, they're just different masses. And so they'll do these measurements and they'll build this calibration curve. And then when they have a sample that they're trying to verify, they measure the unknown sample or the sample they're verifying. They'll put it on this curve to see what the mass is and then see if that mass agrees with the mass that's declared. And one thing I kind of want to point out is you're not kind of going in a lot of times and they don't just have like an unknown item laying there. This isn't nuclear forensics. You're not going in and they're not saying, oh, we have no clue what this material is. Like, we want you to come in and tell us what it is and what the mass is. What the IAEA and safeguards do is we're trying to verify declarations. And so you're going in and you have a declaration. You're supposed to know how much it is. You're supposed to know what it is. And we're trying to verify that. So when they're building these curves, they have samples that they're measuring that they, have verified before, and then using that to verify additional samples. And so, yeah, it's not so much playing detective as, we're just making sure everything, matches up within, statistical uncertainties. Okay, and then I won't bore you with the equations on the left, but they just use an algebraic fit to the data and then use that to propagate all the uncertainties and everything associated. All right, next slide, please. All right, so now we'll get into some of the measurements we did. So the first thing we wanted to do was say, okay, let's do the traditional method. So let's do an active doubles calibration. This is looking at the doubles count rate. So when you do active interrogation, the interrogation source is an alpha N source. So remember, those neutrons are independent and they have no, coincidence rates. And then when we're inducing fission, those fission events will cause, us to measure coincidence count rates, and that's what we use on that curve. So I should have mentioned that in the last slide more clearly. But yeah, so we build these curves. You can see in the blue, that's the uranium-233. And again, because the samples we have, you could kind of build up that mass. We were able to do a very, maybe even in some ways too fine of a very small steps to build that curve up. And then in green, you'll see HEU. What you'll notice is that those curves are pretty much on top of each other. And if you look on the right-hand side, that was building a calibration curve using a mixture of the two triangles. So a 1-to-1 triangle ratio, so about a 4-to-3 mass ratio. And so that got our fissile mass, total fissile mass, up to about 140. And if you were to put all of these three lines on top of each other, they're pretty much all fall on the same path. You can, some might say, hey, the highly enriched uranium curve looks like it might start to go down a little bit, but that was the limit of the mass we had, and so we weren't really able to extend that any further with experiments, at least, to determine if that that difference will continue or if it's just statistical. And so and that's something we'll talk about later, is how we can potentially extend these. And so you'll see, okay, well, calibration curve, you can build a curve, and that's great, but all you get out of this is, the total fissile mass. So, which can be useful. You can say, hey, we know that this is about 80 grams of fissile material, but that doesn't help you verify what the isotopics are. So one challenge we were kind of looking at is how would you distinguish 233 and 235? And so, and this overlap happens because the two cross sections are very similar. There are a few resonances that we're kind of looking to exploit. But initially, when we did measurements, and this is in thermal mode. So if you remember anything from about 20 minutes ago, this had no cadmium in it. So let's see. Yeah, so it had no cadmium, so we're getting the entire spectrum of neutrons, which is interesting because, again, thermal mode is generally best for anything less than 100 grams. So once we kind of get above that, you see the curve starting to flatten, and when you get to much greater masses, self-shielding will be pretty, and the penetration of those interrogation neutrons will decrease. Okay, next slide, please. So the other thing we were able to do, because there is a passive signal with no interrogation sources, is do a passive calibration curve. So this was just looking at their uranium-233. If we measured the highly enriched uranium, we did, and there's statistically no counts above background. And so you'll see a pretty linear fit for this. Again, these are all, or mostly, I should say mostly, alpha N neutrons, which again, remember, are independent of each other. So when you look at the plot on the right-hand side, this is interesting because you'll see the doubles, or the coincidence count rate, is increasing as a function of mass. And so what that's telling us is some of those alpha N neutrons are inducing fission in the sample, and so we're measuring some of those coincidence neutrons. If you look at the y-axis, it's a very small number, so it's not really, we can definitely see that trend, but it's important to note that that's, out of all of our signals, it's probably the very lowest. But it's interesting because how active interrogation works, is you have these external neutrons that you're introducing into the system to cause more fissions to happen. So this is essentially, we call it self-interrogation. So the item is creating alpha N neutrons, which can then induce more fission in the sample, and then that can be used to potentially quantify the mass. This is something that may not be super useful at lower masses because you'll see the signal is pretty small. And if you have, high background or other things happening, depending on the environment, might not be the best measurement to perform. But if you have larger samples, the signal could get to a level where it becomes useful. This is also something that could be useful if you're looking at physics models of the material. All these measurements can come into play. All right, next slide, please. Okay, one thing I want to emphasize, and I'm not taking credit for this, but the project that this is a part of has a big emphasis on complementing experiments with simulations and then using our experiments to validate and inform our simulations, because there's limits on what materials you have to actually perform experiments on, and it's pretty expensive to perform a lot of the experiments and very time consuming. And so we supplement this with a lot of simulations. And so one of my colleagues at Oak Ridge National Lab, Richard Reed, he's done extensive simulations of a lot of the experiments that we did and the detector. One thing I want to point out, since it wasn't in the previous diagram, is that if you look at the model on the right hand side where those kind of red lines are, that's where that cadmium liner goes that we mentioned, so along the cavity and then above and below those end plugs. And so when we did our first round of experiments, which we did 3 total experimental campaigns, we got the results on the lower right hand corner. So you'll see all the little dots, those are our experiments or measurements, and then you'll see the lines kind of look like highlighter. Those are the simulation data that was validated or matched with these experiments. And so what Richard was able to do was then start kind of messing with different parameters in the detector to see how that could potentially influence the results that we were seeing. And one thing that we saw that was really interesting is that, which we didn't really expect this, was we expected pretty much in any mode that those calibration curves would fall right on top of each other. And generally with this kind of amount of mass, the signal from the thermal mode is on the order of 10 times stronger than in fast mode, so with and without the cadmium. So that's one of the reasons we had done those initial measurements in thermal mode. But when he did the simulations, he said, this is the upper left-hand plot right there. You can actually see those curves split, which can be extremely useful, again, if you're trying to determine the ratio or how much 233 versus 235 you might have in a sample. And so he did the simulations and we saw this result, and we didn't really have any experiments to kind of validate that because, I mean, we had done all of the measurements without that cadmium liner. So we ended up going back to say, hey, we don't need to do a super long, several week campaign again. We just want to see if, what we're seeing in simulations is actually, happening. And so if you go to the next slide. We went back and did additional measurements of the materials in fast mode with the cadmium, and we did in fact see a split in the 2 curves. So on the left hand side, you'll see the highly enriched uranium. Again, for time's sake, we didn't get all the same points as we did the first go around. Each of these measurements For the first campaign, they were all 30-minute measurements. For this one, because the signal is significantly lower, these were all hour-long measurements. And if you look at the y-axis, the count rate is about 10 times lower than that first curve I showed. So on the first curve, we were seeing, 200, 300 on the upper end. Here you're seeing, maybe 20, 30. But you do see a split in these two curves. And so, I don't think I have it on here. I mentioned before the cross sections of 233 and 235 are pretty similar, but there is a resonance right above the thermal range, which also happens to be right above that where the cadmium liner, where the energy cutoff for that is. And so when the cadmium liner is in place and you're getting rid of a lot of those thermal neutrons, we're mainly interrogating the sample with neutrons in the higher energy region in which that resonance occurs. And so that's, we're working on verifying that is indeed the source of the difference, but that's kind of the working theory. But again, it's good because we can use these differences to kind of tweeze out information about the source and then use that to verify the material. All right, next slide, please. So I just wanted to give kind of an example of how you would quantify, quote unquote, unknown source. So on one of the last days of the campaign, we said, hey, it'd be cool to just kind of do a random measurement. Like they went in another room and built a source. I didn't know what how many of each material were in it. And we performed a series of measurements, passive and active measurements, and then said, hey, could we use this to determine what's in here if we know it's some mixture of 233 and 235, generally within, less than 200 grams. So first thing we did was, so we did both. So we performed the passive measurements. We did both of these in thermal mode. This was part of the first campaign, and built that passive calibration curve. And so we use a singles rate to predict the 233 mass, since our passive rate only comes from 233. And then we used the active measurement. Again, we built that calibration curve, got the doubles rate or the coincidence rate from our quote unknown source, and then used the curve to determine that mass. And so it ended up being 36 233 triangles and 24 HEU. And so when we use the active curve in thermal mode, so that's the one where they fell on top of each other, we could use that to determine the total fissile mass. So that's both 233 and 235. And so we predicted that to be about 108.4 grams, plus or minus 2 grams, when the actual total fissile mass was 109. So great. That's, pretty good agreement. It's within one uncertainty. There was a slight interesting thing that happened with the 233, because our known U-233 mass was a little less than 72 grams. But when we used our passive signal to predict the mass, it ended up being high by about 2 grams. And that was not within, one sigma. And so the current theory is that this passive curve was built with only uranium-233. So there's no HEU. And you might say, hey, well, HEU doesn't have a passive signal anyway, so why would that matter? If you'll also remember, U-233, because of that alpha N neutron source, it can interrogate itself, even if it's at a very low level, and produce additional neutrons from fission. And so when you add in additional fissile material, so 235, you're not adding in any more signal from alpha N neutrons, but you're adding in more material that could potentially be interrogated and fissioned by those alpha N neutrons. And so it's a very slight increase in the count rate, but that could be a potential factor in there. And so that's why when you're building these calibration curves, it's pretty important that the curves are representative of the sample you're trying to verify, as in they're of similar isotopics, because those isotopics do impact your accuracy using these curves. All right, next slide, please. All right, so I'm going to wrap it up here. This work is ongoing, and the other thing that we are looking at is using more physics-based models, and some of the experiments we've done to use that to do some of the mass quantification and isotope verification. And so that's an ongoing effort at the moment. When I finish my thesis, you can email me and I'll send you a copy. But in conclusion, development of safeguards techniques for 233 is needed. Again, it's not just for safeguards, but general material control and accounting. Neutron NDA techniques, they're kind of our best method and show the most promise at this point in time. Methods are under development using different combinations of signatures, so passive, active. Again, I mentioned this earlier, there's colleagues of mine looking at other signals too that can complement the measurements and methods that I'm looking at. And so some unique combination of these signatures can be used to determine mass and isotopics of these materials. And again, for any advanced reactor people who are out there thinking, well, the material isn't just going to be 233 or 235. We also know that, and so it's important to keep in mind that as we see different materials that are representative of what we might see in future fuel cycles, that some of these methods are able to be extended and account for the presence of other isotopes. And so yeah, we are thinking about it, but again, we need to know what those materials might be in order to develop safeguards methods for them. So I will end there, and I thank you for your time and attention. And I hope it wasn't too off the wall. So thank you for being here.
Thank you, Madeline. If you have questions, go ahead and type those in, and we'll take those in just 1 minute. While questions are coming in, we're going to take a quick look at the upcoming webinar presentations. In January, a presentation on revolutionizing nuclear engineering education, developing virtual labs for neutron detection, Geiger counter, and reactor experiments. In February, the analysis of reactivity loss of the Phoenix core cycles for the experimental validation of the Darwin FR code package. And in March, an overview of the Canadian R&D capabilities to support advanced reactors. We do have a few questions in. Can you describe the physics that gave rise to the nonlinearities at low mass values and the coincidence rates in the AWCC calibration curves?
Yeah, just give me a second. Okay, you said the physics reasons for why we see the nonlinearity?
Correct.
Okay, yeah. Let's see. Okay, so that doubles count we were seeing in theory is from the fission neutrons that are being induced in the sample from some of those alpha N neutrons. It is interesting because when we look at you're thinking the active calibration curves, you generally see the curve going down and kind of decreasing. I think when we're increasing the sample mass, a lot of that has to do with the geometry. And so when we have a lot of the smaller sample, there's less probability of those alpha N neutrons either directly interrogating the sample or leaving the sample and then coming back to interrogate it. So I would say that a lot of, and you can argue, but I would attribute to that nonlinearity to be more from geometry than anything else, the geometry of the sample.
Thank you. What is the minimum mass threshold that can be detected?
So our lowest sample we had was about 2 grams. The uncertainty on that, so we're trying to get the measurements to be within a target value of about 1 gram. But the lowest sample we were able to measure was 2 grams. So I would say 2 grams, but the uncertainty on that might be not great.
Thank you. The techniques discussed today are based on sample measurements. Do you see the need to implement sampling methodologies in liquid-fueled molten salt reactors to use these techniques? What is the status of development of inline safeguards related measurements for liquid fuel advanced reactors?
Yeah, so this is, I think, probably the most kind of question we get asked a lot of times is, what about the molten salt reactors? Because a lot of the work we are focusing on, solid samples and sources. I do not personally work on inline sampling. However, techniques like this, like active interrogation, could potentially be used in some sort of inline measurement. But I don't really have a great answer to your question, other than it's something where I know others are looking into. If you do want to follow up, I can try and see, find people who are working on some of that to point you in that direction.
Thank you.
Thank you for your question.
On one of the earlier slides, you show the mass limit for plutonium, but it is a bit confusing. Could you please clarify?
So the table I had with the 3 different isotopes, the plutonium, U-233, and then the 235, those were significant quantities. So that's the amount of material that, if the IAEA is, doing verification measurements and tracking material, and statistically you see more than like 8 kilograms of plutonium missing, that's when they can't say with certainty that, material wasn't potentially diverted. That's the amount of material we're really worried about being unaccounted for. So that's what was the word you used? It's not a mass limit, it's a significant quantity. And so that's just something for safeguards that's defined by the IAEA.
Thank you. Thank you for your presentation. Could you please tell the effect of the existence of U-232 as gamma source?
Yeah, so one thing that you'll hear a lot when it comes to safeguarding U-233 is that it's, quote, proliferation resistant, because the presence of 232, even in pretty low quantities, still can have a really high radiation field associated with it, which is actually one of the reasons it wasn't pursued, for use in weapons, because it makes the material a lot harder to handle. And so, yes, so the effect of it being there is that, one, we can't use, gamma to quantify the 233, and then 2, it does inherently have proliferation resistance, but I want to emphasize that doesn't mean you still need to be able to measure it and apply, safeguards or accountancy measurements on the material. And so, if anything, the effect is that it sometimes makes handling and measuring and quantifying materials with 233 harder, because you have this gamma source in it.
Thank you. Good presentation. Thank you. On slide 11, do you mean that the plutonium must contain less than 80% by weight Pu-238? So let's take a look at slide 11 and see if that doesn't help taking a look at it.
Yeah, that's just what's defined as a direct use material. Yeah, so less than 80% 238. So that's looking at the isotopics. Just like for HEU, that's only when defined as when there's more than 20% 235. Yeah, okay. So if it's greater than 80% 238, it falls into a different category, and that number will be higher.
Thank you. So a follow-up to a question, does it affect neutron measurement, thinking that H3 tubes may be affected by the gamma? So we may have to go back and see what that earlier question was.
Oh, the effect of 232. Yes. It's so the sources that we had don't really have a high amount of 232. I have two kind of answers. One is that we are looking at how lead shielding would affect the neutron measurements, because in a lot of cases, these materials would be in lead shielding, so the gamma dose may be reduced to the point where, you know, we can still do these traditional methods and they're not highly affected. But one thing that my colleague Oscar Sierfis is looking at with some of the different measurements that he's doing is using a helium-4 detector. And that's really important because it's insensitive to gamma rays. Again, if that's something you're interested in, I would go look at that. But we are exploring other neutron NDA methods that, you know, would be insensitive and not affected by those gammas. So I just specifically don't work on that. But as part of this collaboration, there are other people who are looking at other instrumentation that would overcome that limit.
Thank you. Can you give some suggestions for using U-233 in molten salt reactor, taking safeguards into consideration?
I think the biggest suggestion is that if you're looking to have 233 in a molten salt reactor is to start engaging with the safeguards community and the labs, because an important factor is, you know, what form are the materials taking and how much. And so even if it's like we need to just know how much is going in and then eventually how much is coming out, I don't know if that might include inline monitoring, but there are programs in place through NNSA called ARISE to support the development of safeguards for advanced reactors. And so if people are designing reactors that have 233 or other safeguards, you know, safeguards, applicable materials in them, they can reach out, and people at the laboratories, you know, like Los Alamos or Oak Ridge or wherever, can come and like help develop, think about what safeguards methods could be applied to different designs and materials.
Thank you. Is there a need for this much safeguard for nuclear proliferation these days, given precision bombs are available to militaries that can do damage at the targeted real estate, which reduce the need for nuclear bombs?
That's a very interesting question, and I have personal opinions on this, so I'm going to be careful with what I say.
I almost avoided the question to begin with, but
the one thing I would say is even if you take proliferation out of the equation, because I kind of agree, I think safeguards also does kind of, it's a level of accountability, and you hear the word, you know, deterrence a lot. If someone's kind of watching you and verifying what you're doing, you're less likely to try and do something you're not supposed to be doing. But the other thing to keep in mind is all of these methods, when it comes to nuclear material, whether you're going to use it in a bomb or not, you still want to know where it is and how much of it you have. And so safeguards aside, just general material control and accountability in all of, you know, nuclear processes, I think is extremely important. And as a lot of those materials and processes, you know, there's more and more, it's again important to know where that material is and in what form. And so I can't say if I specifically agree or not with you. I think there are other uses of these methods, and I would say even with some of the, you know, online monitoring and processing, sometimes the operators and you know, facilities benefit from those measurements as well, because if we detect something's going wrong, they might not be trying to divert stuff for weapons. There might actually be something going wrong, and that still needs to be detected.
thank you. think that's the line. I think that's the questions that have come in so far. Madeline, I can't thank you enough for a
Berta?
wonderful presentation. Yes, ma'am.
Yeah, I would like to add something to all the questions we had on molten salt reactor system. Ben CPT from Sandia National Laboratory has given a GIF webinar presentation on safeguards on advanced reactor system in March 2023. So I encourage the people who have questions on molten salt reactor to watch the webinar. It's on the GIF portal at www.gen-4.org. Ben CPT is the National Technical Director for the cyber security and safeguards of advanced reactor system for the Department of Energy, Office of Nuclear Energy. Thank you, Berta.
Yeah,
Thank you,
and that's
Patricia.
that's the same one I mentioned at the very beginning. Yes, I would definitely recommend people watch that if they're interested.
Yeah, thank you, Madeline.
So again, Madeline, thank you. I am always impressed. I think the future of the workforce is in good hands when you think of the next generation being represented by people like Ms. Lockhart. It encourages me that we will leave this legacy in good hands, and I appreciate your talents and expertise. Thank you for sharing it today.
Yep, thank you for having me.
I don't see any more questions. Other than that, mention to Ben, do you have any closing thoughts, Patricia?
Yes, first of all, thank you so much, Madeline. I wish you the best for your PhD. You're in your 4th year, so it's going to come soon. And again, thank you very much for presenting this webinar today. And since we are approaching the end of this year, on behalf of the Gen 4 International Forum, Education and Training Working Group, I wish you all a happy season. Thank you so much, Berta, again, and all the best for us, for everyone, for this new year 2024. Thank you.
Thank you. Bye-bye.
Goodbye.